All right, so good morning. It's time to talk about electron configuration, and that's going to require a quick review of orbitals. So let's jump right in. Okay, so why do we talk about electron configuration and orbitals? We talk about them because they help us to understand the reactivity of the various elements. So first, let's just do a quick review of what the orbitals are. We remember that they're s, p, d, and f orbitals. The orbital describes that three-dimensional shape in space where the electron has a 96% probability of being found. And we remember that at each energy level, we add a new set of orbitals. And so at the first energy level, the only thing that we have is the s orbital, and that's that spherical shaped orbital. At the second energy level, we have both the s, the spherical orbital, and the p orbitals. And when we get to the p orbitals, there are now 3 different p orbitals. They have the same shape, but they have different orientations in space. When we get to the third energy level, we have s and p and d orbitals. And the d orbitals, some of them actually have different shapes as well as having different orientations in space. So 1 s orbital, 3 p orbitals, 5 d orbitals. When we get to the fourth energy level, we do add in f orbitals, and there are 7 f orbitals. They have both different orientations in space and different shapes. Each orbital can hold 2 electrons. This means that the 1s energy level, any s orbital can only hold 2 electrons. When we reach the levels that have p orbitals, each p orbital can hold 2 electrons, which means that overall the p orbitals can hold 6. The d orbitals can hold 10, and the f orbitals can hold 14. So we have our p orbitals, we have a px and a pz and a py configuration. So this is again just that orientation in space. Please remember that the orbitals are areas in space where we are likely to find electrons. This is not a path for the electron to follow. This is a probability map. The d orbitals have a slightly different shape. These are sometimes called the double dumbbells. They certainly look like 2 peanuts crossed in most cases, although the one looks like a pacifier. All right, so how do these fill? So electrons fill the lowest available energy stage. So we fill from the lowest energy level, overall level is 1, all the way up to an overall energy level of 7. They start with the s orbital. When we move into the levels that have both s and p, so starting at energy level 2, s will fill completely before any electrons are placed into p. Similarly, when we get to the fourth energy level, so when we get to the third energy level, 3s fills first, 3p fills second, but then you'll notice that we move into the 4s orbital before we start filling the 3d orbital. So when they are unoccupied, the 3d energy level is slightly higher than the 4s energy level. Once they're occupied, that energy starts to shift a little bit. And so that means that they fill 4s first, but they empty 4s first as well. So when we start talking about formation of ions, the s orbitals empty before the d orbitals. This particular image is kind of showing you the order in which they fill: 1s, 2s, 2p, 3s, 3p, 4s, 3d, then 4p, then 5s, then 4d. If you ever get confused, you can always look at a periodic table, and the periodic table shows you the order of the filling, because you can see the S block fills before the P block, and the S block also fills before the D block. So that D block is that central block of the periodic table, the ones we typically think of as the transition elements. And then the F block is the lanthanides and the actinides, the ones that are normally pulled out below the periodic table. Okay, so when we talk about electron configuration, we have lots of different ways of writing it. The most common way is either electron configuration notation, which you see in the second column here, or the noble gas notation. The noble gas notation is kind of a shortcut notation. It allows you to write the noble gas that comes before the element whose configuration you're writing, and then only those electrons that come after that noble gas. So if we look at lithium as an example, it has the configuration of helium plus one more electron in the 2s energy level. So we write that as helium in brackets 2s1. The other format is what we call orbital notation. Orbital notation shows each electron in the orbital. So we have in lithium 3 electrons, 2 of them are in the 1s and 1 of them is in the 2s. And you'll remember that Hund's rule says that 2 electrons in the same orbital must have opposite spins. And so that's represented by the up and the down arrows. So we can see this for all of these. I do want to point out that as we fill orbitals, you remember that each of the orbitals at the same energy level will receive 1 electron before any of them receive 2. So this is kind of like social distancing for electrons. So you'll notice here in carbon that it has 2 electrons in its 2p energy level, but that they are each occupying different p orbitals. So you can see that at the 2p energy level, for example, in carbon and nitrogen, that each of these 2p orbitals receives 1 electron before any of them receive 2. And so it's not until we get to oxygen and we have 4 electrons in the 2p orbital that any of those 2p orbitals have 2 electrons in them. And the reason for that is that even though the orbital is not a physical region in space, it does put the electrons closer together to put them into the same orbital, and so you're increasing the amount of repulsion. So these electrons are staying as far away from each other as possible until you have to put 2 of them into 1 orbital. All right, so now we're going to do some practicing, and so we'll stop here. Okay, let's practice writing electron configurations. So the first thing we need to do when we want to write electron configurations is find the element on the periodic table. So we're going to take our first example and we're going to find iron. So here's iron on the periodic table. It's element 26. We know that it has 26 electrons. But the first way that we're going to do electron configurations is that we're going to practice using the building up method. And so here's iron. We're going to move through all of the orbitals that are filled before we get to iron. We need to remember that this is the S block, this is the P block, and this is the D block. So we're going to start at the beginning. We know that 1s is our first occupied orbital. And because we have to go through both of these blocks in order to get to it, we know that it's full, 1s2. Next, we move down to the second row. This is the S block. We have to move through both of these. So 2s is also full, 2 blocks. Now we have 2p, and we're going to fill that. So it's 2p6. And now we have 3s, that's filled. So we're going to add a 3s2. Now we move all the way through the 3p orbital. So that's 3p6, and then we're going to move through the 4s orbital, and here's where we have to remember the way that this works. So we know that energy level 3 has both an s, a p, and a d orbital, but that the 4s fills first. And the periodic table helps us to remember that because we go 1s, 2s, 3s, 4s, But we know that this, even though it's in the fourth row of the periodic table, is the 3D block. So let's count and see how many electrons are in our 3D block. So 1, 2, 3, 4, 5, 6 electrons in our 3D block. 1, 2, 3, 4, 5, 6. So we're going to write 4d6, and that's iron. If you want to confirm that you've done it correctly, you can always add up all of the electrons. So 2, 4, 10, 12, 18, 20, 26 electrons, and this is element number 26. So we're good for iron. Now, let's do another one just for practice, and we'll do it a different way. This is the way that I usually do these, but the right way is whichever way works for you. Okay, so here's calcium. Okay, we're going to write the electron configuration for calcium. Calcium, the way that I look at this, is in the fourth row in the S block, and it's 1, 2 into the S block. So I'm going to start at the end, and I'm going to write 4s2. Now I know that in order to get there, if calcium is in its ground state, that all of the orbitals prior to that are full. And so I'm going to write 3p6, 3s2, 2p6, 2s2, 1s2. And now if we count 2, 4, 10, 12, 18, 20, calcium has 20 electrons. This is the electron configuration for calcium. Now, what's different when it is an ion? Not a lot. Okay, when it's an ion, generally speaking, if it's an S block or a P block, so S block or P block element, then its final configuration is going to be a pseudo-noble gas configuration. So let's look at the chloride ion. So here's chlorine here. We know that chlorine normally has 17 electrons, but we also know that when chlorine forms an ion, it's going to add an electron so that it has the same configuration, electron configuration, as argon. So chlorine normally is in the third row, P block, 1, 2, 3, 4, 5. So we would normally write 3p5 at the end, but we know that chlorine is going to add an electron, and so it's going to be 3p6. So 1s2, 2s2, 2p6, so 1s2, 2s2, 2p6, 3s2, and now 3p5 plus one extra electron, 3p6. This is the electron configuration for the chloride ion. It's also the electron configuration for argon. It's also the electron configuration for the sulfide ion. It's also the electron configuration for the phosphide ion. So we call those isoelectronic. Oops, there's the configuration. So, hopefully you guys feel comfortable with that. Let's talk about the next step. So what if we have a electron configuration and you're asked to determine the element? In that case, I definitely recommend just looking at the end. Okay, so if the ending is 3s1, so we're going to move down to row 3. This is the S block. 3s1 is right here. That would be sodium. Okay. In a similar way, if it's 3p5, here's the 1, 2, 3, P1, 2, 3, 4, 5, and that's chlorine. If it ends in 3d7, so now D block, remember, is one row behind. So this is the 3D, 1, 2, 3, 4, 5, 6, 7. That's going to be cobalt. And our last example ends in 4p2. So 4p, 1, 2, that's going to be germanium. Okay, so then the next step is to look at electron configurations and see if the element is in a ground state, meaning that all of the electrons are in the lowest possible energy state, or if it is in an excited state. So let's take a moment to think about that. Okay, so let's talk about looking at electron configurations and determining if any of them are in the excited state or in the ground state. So in order to do that, we need to know what our normal pattern is for filling, and we've talked about that. So we're going to look at these configurations and we're going to see, is each orbital filled before the next orbital receives any electrons? So if we look at this one, 1s2, that's full, 2s2, that's full, 2p. Now a full p orbital would receive 6 electrons. This one only has 5, and yet we've moved on to 3s. And so we know that this is in the excited state. If it were in its ground state, it would be 1s2, 2s2, 2p6, 3s1. So let's look at this next one. 1s2, that's full. 2s2, that's full. 2p6, that's full. 3s2, that's full. 3p3. This is in its ground state because each orbital is filled before the subsequent orbital has any electrons. So we're going to scan all the way through S2, S2, P6, S2, P6, and now we have 4S1, 3D1. So if this were in the ground state, we would have 2 electrons here and no electrons there. So this is in the excited state. And we're going to rewrite this as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, and one last one. We're going to scan through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. If this were full, it would have a 10 here. So we know that some electron has been promoted to the next energy level. This one is excited. If this were in its ground state, these last 2 numbers would be 3d10, 4p2. So let's look at identifying these elements. This one ends in 3s1. So we're going to have our periodic table. And we're going to go down 1, 2, 3, and 3s1. So this is sodium. This is in its ground state. It ends in 3p3. So here's 3, p, 1, 2, 3. This is phosphorus. All right, the next one, we've said in its ground state would end in 4s2. So 1, 2, 3, 4. Here's the S block, 2. That's going to be calcium. And our last one ends 4s2, 3d10, 4p2. So we know we're in row 4, S2, D10, P1, 2. Now we're back at germanium.